Welcome to today's webinar titled Microfluidizer Technology for Graphite Processing and Formulation of Graphene-Based Conductive Printing Inks. I'm Kelly McCabe, an Applications Engineer at Microfluidics, and with us today is Dr. Stephen Hodge, a Research Associate at the Cambridge Graphene Center. Steve is in the Nanomaterials and Spectroscopy group at the Cambridge Graphene Center, teaching fellow in the EPSRC Center for Doctoral Training in Graphene Technology and Bi-Fellow of Murray Edwards College. He has particular interest in the chemistry and physics of the nanomaterials, including fullerenes, carbon nanotubes, graphene, and many other two-dimensional analogs. His current focus is on the scalable production of these enabling materials for mechanical, optical, and electronic applications. We will begin today's webinar with a quick overview of Microfluidics as a company, the microfluidizer technology, and processors. I will then turn it over to Steve to talk about his research with formulation and processing development of graphene. Finally, at the end, we will hold a Q&A session. Microfluidics has over 35 years of experience serving the nanotechnology industry, utilizing the patented interaction chamber technology to produce high shear fluid processors. We are located in Westwood, Massachusetts, right outside of Boston, with a global presence in nearly 50 countries and thousands of processors worldwide. In 2011, IDEX Corporation acquired Microfluidics and grouped us together with Quadro Engineering, Fitzpatrick, and Matcon to form the Materials Processing Technologies platform. Microfluidizer processors are used in research and development and manufacturing environments, generating critical results for many applications from pharmaceutical and biotech industries to food and nutraceutical, as well as chemical and cosmetic industries. We use our vast applications and design experience to help our customers achieve their successes. So here are a few of the things that we do very well, which include nanoemulsions that need to be sterile filtered, as well as liposomes. We have experience with polymer nanoparticles, as well as cell lysis for biotech applications with high protein recovery. We are very efficient at deagglomeration and particle size reduction, such as the shear exfoliating of graphite to generate graphene, which Steve will touch base on after this, as well as carbon nanotubes and nanocellulose. We can also achieve molecular weight reduction, such as the molecular weight reduction of polysaccharides. Here below are a few examples of the microfluidizer processors that we offer. We have a wide range of processors, from the low volume bench scale lab machines that can be scaled linearly up to production machines. Here you see the basic schematic of a microfluidizer, where material will be drawn in through your inlet reservoir there on the left, and it will be pushed out at constant pressure through your fixed geometry interaction chamber and then out through the heat exchanger. This method provides continuous processing, as well as the ability to work with high viscosities and high solid content, as well as the use of the heat exchanger can help you work with a wide range of temperatures. Here, the fixed geometry interaction chamber is the core of our technology and comes in multiple shapes and sizes, including the Y-type interaction chamber and the Z-type interaction chamber, where the Y-type is primarily used for liquid to liquid only, and the Z-type is great for anything that contains any solids, where your impact zone is up against a wall, where the Y-type, the two streams impinge upon each other for these smaller droplet particle sizes that are found in nanoemulsions. Another advantage of the interaction chamber design is the linear scalability. When scaling up, we simply put multiple microchannels in parallel to ensure every microliter of material is still being processed under the same high velocities, shear rates, and impact forces. This ensures that the production microfluidizer processors will achieve the same consistent, uniform results as the large-scale units. To summarize, microfluidics technology is quite unique, utilizing constant processing pressures through fixed geometry interaction chambers. A resulting benefit is guaranteed scalability from lab scale to production scale using multi-slotted interaction chambers, as well as very small particle size and very narrow distributions, which provide excellent batch-to-batch repeatability. Microfluidics technology is also cGMP compliant and has clean in place and steam in place capabilities. Here is a quick glance of the Microfluidics product portfolio, which offers a wide variety of microfluidizers, including several lab machine designs, as well as pilot and production scale machines. The microfluidizer processors offer a wide range of flow rates to meet your specific needs. And now, without further ado, I will be handing this presentation off to Dr. Stephen Hodge. Thank you so much.
Hi, and welcome to this webinar, and thank you to Microfluidics for hosting it and giving us this opportunity to talk about some of the research we're doing on microfluidizer technology for graphite processing. I'm going to start by giving an outline into the presentation. So I will begin with what is graphene and talk about the structure and properties that make it such an exciting material. I will talk about the main exfoliation methods, so how we can go from graphite, the bulk structure, and down into thinner and thinner graphene layers. I will talk about our motivation for printing graphene as a conductor and looking at conductive inks and some of the applications that go with that. And so I'll talk about some of the opportunities that we are exploring. And I'll give a final future outlook, so looking at some materials beyond graphene and how they might be also important for future technologies. So graphite is a naturally mined material. It can also be synthesized in a lab, in a furnace, or it's often a byproduct of some industrial processes. Essentially, we have a carbon framework arranged in a hexagonal structure, and we have bonding in the plane, which is very strong. These are covalent bonds. Between the layers, we have very weak interactions, which mean graphite layers are often sliding over each other, which is why we have a good property as a lubricant. And essentially, when we go down to the single atomic layer, we've got rid of all of these weak interactions in between the layers, and we have essentially a very strong material. So something which can be a few hundred times stronger than steel. So you can look at this cartoon here of an elephant standing on the tip of a pencil on a sheet of cling film. It shouldn't be enough to break through the graphene structure. In terms of its electrical properties, now we know there are many conventional materials, insulators, semiconductors, which have a gap. This is known as a band gap. So for these materials to conduct electricity, we need to move electrons into these top states. So we have to overcome this band gap. Metals, however, don't have a gap, which means they're always conducting. And graphene has a unique structure, which means it also behaves like a metal. Essentially, we can have, again, a material on a single atomic layer can be 10 times more conductive than copper and have much better conductivity of heat, which make it very interesting. In terms of the speed of the electrons through graphene, they're 1,000 times faster than they are through traditional silicon semiconductors, which are used in all of our mobile devices and computers. So to harness some of these important properties and make use of graphene's potential, we need some way of manipulating and depositing these graphene structures. So one way we can do this is producing conductive inks and then printing them using different techniques to produce conductive circuits and electrodes. So the performance of these devices are typically compared using their sheet resistance. So for applications, for example, electrodes in organic photovoltaics or OLEDs, we need materials with sheet resistance less than 10 ohms per square. For radio frequency tags, we need something on the order of less than 5 ohms per square. So looking at traditional graphite-based conductive inks, these give a sheet resistance normalized to 25 microns of around 10 to 100 ohms per square. If we look at metal-based inks, so silver or copper, aluminium-based inks, these we can achieve down to around 0.01 ohms per square, so much higher conductivity. But there are issues with electromigration. There are cost issues, so silver is very expensive. Copper often oxidizes with time, and so it may degrade. And also there are some toxicity issues, so recycling these materials is not so straightforward. They cannot just be thrown away as they will lead to some environmental toxicity. With graphene-based inks, so the best performance that we've got so far is around 2 ohms per square at 25 microns thickness. So until recently, the challenge for graphene has been with the scalable production methods, and that's where microfluidic production has really helped and now should help us to be able to drive down the cost of graphene inks and graphene production. So I mentioned already some applications, for example the electrodes in OPVs and OLEDs and RFID tags. Another big area is energy storage. So we're all using graphite lithium-ion batteries in our mobile devices. So if we can go from graphite to graphene, we have a material with higher surface area, higher conductivity, so we can charge and discharge our batteries faster, and also we can store more charge in the first place. Sensors are also a key area. So graphene can be used because not only does it behave as a conductor, but we can also have some impressive changes in its resistivity or conductivity, especially in different environments with different gas molecules, or if we apply some strain to the material, we can see changes in its conductivity. Again, printed circuits and interconnects are obviously a key area where we might be able to replace other copper wires. And printing onto textiles, we hope to be able to start to develop wearable electronics, especially printed sensors that can be integrated into clothing. So going from graphite to graphene, the first thing we have to consider is which method we want to use, and then also the starting materials, the raw materials. So there are three main approaches to actually exfoliate graphite down into thinner and thinner layers. The first being mechanical exfoliation, so that's taking a piece of Scotch tape and manually peeling away and exfoliating the layers from a powder. The second approach is a more chemical-based approach, and that's called graphene oxide production. So here we would do an acid-based synthesis or acid-based reaction on the graphite powder, which then leads to all sorts of functional groups being added. So typically oxide groups, carboxylic acid groups, which can make the graphene more soluble. But in fact, we leave a lot of defects behind and added to the structure, which can limit some of the important properties that we're trying to harness. So we minimize the electrical conductivity. We may lose some of the mechanical strength. The third approach, which I'm going to talk mainly about today, is liquid phase exfoliation. That's a process which can give better quality. It's low cost because we're starting from graphite as the raw material. It's a very scalable technique, and we can often have better purities of the material. We don't necessarily introduce all sorts of functional groups on the surface. So this pie chart shows the natural sources of graphite throughout the world. So we have mainly it's found in China, North Korea, Brazil, and a few other countries. So selecting the right starting material is key because it comes in all shapes and sizes depending on the mine. It's low cost, but it has variation of layer thickness, lateral size of the graphene that you can produce from these starting materials. So how do we then do this liquid phase exfoliation? So we start with the graphite powder. We can take a special solvent, or we can use a water solvent with a surfactant. So surfactant can help stabilize the graphene layers once they are exfoliated. We apply some energy, normally in the form of high shear, and we then have a resulting graphene dispersion. In most cases there is a large proportion of unexfoliated material which we then need to separate after, but I'm not going to go into too much detail on this separation process in this talk today. But most of the existing techniques we can compare by the yield of the process, so we can look at the weight of what's dispersed divided by the starting mass of graphite flakes. So every lab that's producing graphene will have a sonication bath. So this process uses ultrasound, which generates cavitation bubbles, and that when they implode, they will generate high shear forces in the solution. So it's quite a localized process. If you want to scale it, you need to use a much bigger bath, but there are issues with uniformity of the production. You can take this one step further and use a shear mixer. This is much more scalable, and you can produce larger batches. But here you have a rotor and stator, which produces very localized high shear. However, both of the yields of these processes are around 1%, so that's why we looked at exploring other techniques. You can do some electrochemical exfoliation. So using graphite as an electrode, you can apply a voltage. Essentially, that charges the graphene layers and causes them to repel each other, and they start to then dissolve into your electrolyte. You can have quite high yield process with very good quality graphene. However, you end up typically with a lot of other inorganic materials and inorganic salts which are as part of your electrolyte, which you need to wash away after to purify your material. The final approach I'm going to talk about is another acid-based approach. This is developed at Rice University, but actually can give graphene nanoplatelets in very high yield, up to 100%, but that's graphene or graphite platelets with 25 nanometer thickness. So I come on now to the microfluidic processing, and this is what's helped enable us to really scale the production of graphene-based conductive inks. So this is the M110P Largescale system. Essentially, this schematic shows the process. So we have an inlet reservoir, and we pump graphite in water with some surfactant through the interaction chamber here, where the high shear forces are generated at the side walls of the chamber. So we are using a Z-type chamber. The graphene exfoliates inside, and then we pass it through a cooling section, and from the outlet reservoir we then recycle the material back through the inlet reservoir. So inside the chamber we have all sorts of fluid dynamics going on. So due to the geometry of the chamber, we are constricting the fluid, and with a water-based system with low viscosity, we can look at the Reynolds number, which is the ratio of inertial to viscous forces, and this number can tell us whether we have laminar or turbulent flow. So in our system we have turbulent flow. We can also, with the help of microfluidics, we've been able to work out some of the other key parameters, such as the pressure losses. So we've also looked at the energy dissipation through the channel, and the most important characteristic is the turbulent shear rate. So we have a value here which is on the order of 10 to the 8 per second. So some previous work on graphite exfoliation showed that you need around 10 to the 4 per second to actually start to peel away layers of graphene from the graphitic structure. So we have a lot of room to play here in terms of looking at other materials that might require higher shear rates to perform exfoliation. So that's quite key for the microfluidic process to have this extra room to play. Another characteristic which defines a turbulent regime is the Kolmogorov length scale. So in a water-based system, what we have is the energy dissipating through different eddy sizes until you get down to this regime, this viscous subrange, which is determined by the length scale on the order of 110 nanometers. So we think this might be a key parameter in terms of controlling the size of the graphene flakes that we can produce. So if we change the viscosity of the system, we might be able to tune this length scale to, for example, increase the size of the graphene that we produce. So this schematic again just shows the process. So as I mentioned, we have graphene or graphite coming in at the inlet reservoir, being pumped through the system. The interaction chamber is where all the exfoliation takes place, and then we recycle. So essentially we go from graphite to graphene flakes. We call them graphene flakes. So these are flakes which are around 7 nanometers thick, around 1 to 2 microns in lateral size, but we are producing them in a 100% yield, and because everything is going through the same process and it's all going through the same interaction chamber and being recycled, we end up with quite a uniform product at the end. So typically we are running the process for around 70 cycles to get the product we want, and I'll go into some of the characterization of the materials following this. So the particles we put in are around 27 microns, and after 70 cycles they're around 1 micron in lateral size. So they go from sort of bulky rock-like structures to very thin platelets. So one of the interesting things, and well, the most promising thing with the microfluidic processor is the scalability. So with our Largescale system, where we have flow rates around 100 mils per minute, we're producing around 6 to 10 grams of graphene per hour. However, if we were to look at scaling this process and go to one of the bigger microfluidic systems where we have 12 liters per minute flow rates, then our production rate can scale to around 65,000 liters of graphene conductive ink per year, or 6.5 tons by mass of the graphene alone. So that's a huge amount of throughput on one microfluidic system. So once we form these dispersions, we formulate different inks for different printing processes. So the most common ones we look at in Cambridge are screen printing, inkjet printing, and flexographic printing. So if you want to have an ink which can satisfy these printing processes, then we can look at then high scalability of printed electronics. So each of these techniques will need different viscosity requirements. They have different throughputs, and therefore can be used to target different application areas, but also what's key is the feature size. So with processes such as inkjet printing, we can print the finest features down to around 20 microns. With screen printing, we're typically getting around 75 to 100 microns resolution when we're printing track widths. So the ideal behavior for an ink, especially for screen and flexo printing, is to have Thixotropic behavior. So this is where, as we apply some shear to the material, it will start to thin. So you have a shear thinning behavior. And once you stop printing and you stop applying shear, the viscosity should rebuild, and you can therefore have a defined feature size. So ideally we want high viscosity at low shear rates. Again, this helps us to stabilize the material, the ink. So this is kind of a graph showing the effect of shear. So different printing techniques or brushing can have different application of shear on the material. So the viscosity should drop, and as we stop printing, we want this to rebuild and again define our printed structure. So we do lots of formulations. So if we want to make a conductive ink, we don't want to add too much material which is insulating. So lots of all these polymers that can help improve viscosity are having a negative effect on the resulting conductivity. So we want to add a polymer which has the lowest weight percentage loading but can give the highest improvement in viscosity. So just screening many different polymers. The best one that we find is working with celluloses. So at 1 weight % loading, we can actually increase viscosity of a water-based system by several hundred times. So you can see this nice shape, which is typical of the thixotropic inks we mentioned on the previous slide. So we can use cellulose as a multifunctional material. It can improve the rheology. It can be a binder for the material. It can also improve the adhesion on certain substrates, and it can help stabilize the graphene flakes in the solution. Here is another rheology plot showing the effect of graphene content on the ink. So as we add higher amounts of graphene, the viscosity again increases quite considerably. So what we're doing all the time is choosing a different combination of graphene loading to polymer loading, which can help us finely tune the rheology for the printing technique. So simple blade coating of these graphene inks onto different substrates, so glass or plastic. We can create different thickness films. We perform annealing just by drying or evaporating the water at 100 degrees Celsius, and we can leave behind different thickness films. We've investigated some of the process parameters, such as the microfluidic processing cycles, and looking at the performance of resulting films. So here we've kept a constant wet film thickness of the ink, and we measure the sheet resistance as a function of these process cycles. So what you can see, after even 5 to 10 cycles, we have pretty consistent sheet resistance. However, it's the thickness of the resulting film that changes. So if you want to go to much thinner conductive films, you might need to process the material for 100 cycles. However, you obviously need to think, are there any drawbacks with the throughput? So maybe if we're processing for such a long time, the graphene production rate will considerably drop. So it's about finding the right balance between process cycles and your actual final product performance. So here you can see a typical coating with the unprocessed material. It looks like rocks, as we saw before. And then for the 100 processed cycles, we have a very flat planar film with quite low roughness. We then look at the effect of graphene loading on the film thickness and on the conductivity that we can achieve. And as you might expect, if we have a high proportion of conductive component, we have much higher conductivity, but we always find there's a critical thickness dependent on the loading. So as we get up to the highest loadings, we can achieve this kind of percolation threshold around 2 micron thickness, so above which we have a pretty consistent conductivity of the material, so it doesn't increase any further. So we're on the order of 10 to the 4 Siemens per meter. And the best sheet resistance we can achieve with these films is around 5 ohms per square. So what we're doing here is just drying, removing the water at 100 degrees Celsius. We're not doing any further annealing. So this is something which is compatible with most plastic substrates and paper substrates. And so we demonstrate more than 10 times improvement in performance compared to the graphitic starting material. But we can also then do further annealing, which is also substrate dependent. So some plastics you cannot heat beyond 100 degrees, but if you're printing on glass or on Kapton, which is another polymer substrate, you can heat these to much higher temperatures beyond 300 degrees. And so again, we can use heating treatments to further improve the conductivity of the printed films. So this is a thermogravimetric analysis plot, and that's just showing at these high temperatures we are starting to decompose some of the surfactant we're using, which is called sodium deoxycholate, and also we are starting to decompose the cellulose. In this case, we're using one called carboxymethyl cellulose. So that's starting to decompose beyond 260 degrees, and we can remove around 60% of that material up to after around 300 degrees. Okay, so those are now giving us performance of 2 ohms per square at 25 microns. So those are the best films achieved to date. So looking at large-scale printing, We work with local companies in Cambridge. One of them in particular is called Novalia. So they're a university spin-out, and they develop their own circuits, conductive circuits for capacitive touch posters. So here we went to a local screen printing press and produced quite a few litres of ink, and we were able to print a few hundred of these posters, which are A3 sized. We can see here we have resolution of the lines down to around 100 microns. So that was just one demonstration that we can make functional posters and integrate them, print them on paper, which can be obviously very cheap and recycled. But then beyond that, we now target radio frequency tags. So here we're looking at competing with typical silver and aluminium based metal antennas. So graphene again has some potential environmental implications. We can recycle these materials, but also we can attach other kinds of sensors to the graphene, or use the graphene antenna itself as a sensing platform, for example monitoring humidity or temperature. So these antennas, we actually can have a reading range now of beyond 10 meters, which is comparing to typical state-of-the-art metal-based antennas. And then another technique we use is flexographic printing. So I mentioned we have another set of rheology requirements, but here we have an ink bath, and we transfer graphene ink onto a roller, which then transfers onto an analox, which has a blade which can then transfer the ink onto a printing plate. So we have our design on a rubber stamp on this cylinder, and then we have our flexible substrate on another roller where the ink will transfer from one to the other and leave behind a pattern. So this is the technique you would use to print newspaper. So it's a very fast process, and we were able to print graphene inks up to around 30 meters per minute. We can also print some kind of transparent grids. So although the inks are quite thick and they appear black, we can actually print mesh structures, which might be useful as electrodes in organic photovoltaics. And again, this technique with line widths can be printed down to around 80 microns. So the resolution is slightly better than with screen printing, but typically the printing thickness is around 1 micron compared to around 2 to 3 microns with screen printing. So we're printing slightly thinner layers. So one of the applications we look at is simple strain sensing. So if you print a graphene resistive track, as you bend it one way, you're stretching the sample. If you bend the other way, you're compressing the sample. So essentially you can improve or decrease the conductivity of graphene just by bending it. So this is a simple demonstration. However, you can go to something more complex, where here we have a multi-layered structure. We're looking at with a graphene back electrode, which is thick and black, but on top we have a transparent graphene electrode. So this is a printed layer, which is a different kind of ink, but we're printing a few nanometer film thickness. And in between that, we've sandwiched it with a phosphorescent material. So when you apply a voltage between these two electrodes, you can make the phosphor light up. So we can make some flexible lighting modules. So here we can see just a schematic, but here's the final device where you can see the light shining through the transparent graphene top layer. So that's just a couple of simple applications that we can do using printed graphene inks. Now, because of the microfluidic process, we found we could achieve very high concentrations of graphene in solution. So what happens when you basically confine these graphene flakes together, as you increase the concentration, they start to align and form liquid crystals. So that's hugely important because you can then control the structure of your liquid crystal, and you can make different structures from this. If we just look at some data we've performed on a synchrotron, this is called small angle X-ray scattering. So I will just show you, as you increase the concentration, so the number here is the loading of the graphene in the ink. You start to see this pattern emerge, which is looking and showing the alignment of the graphene flakes in the solution. So as we approach 80 grams per liter and we can go even further than that with the microfluidic process. We can go up to 100 grams per liter. We have a huge amount of orientation and preferential alignment of these liquid crystals. So what we can make two different processes. The first, we can produce fibers, so we can inject the ink as it comes out of the microfluidizer into a bath of acetone, and what that does is it precipitates the ink in a very fine structure. We can actually grab hold of it with some tweezers and start collecting it on the drum, so we're actually pulling a fiber from this bath. So here you can just see a video showing the continuous motion of this graphene fiber being collected. Okay, so if we look under a microscope, we can see they're around 40 microns in diameter, and you can see the sheets of graphene aligned nicely. So we can produce conductive fibers. We can also change the material. So I will talk a bit about materials beyond graphene, but two of them in particular. One's called hexagonal boron nitride, which is an insulating material. Another is called molybdenum disulfide, which is a semiconductor. And these can also be produced with the microfluidic processor and then turned into functional fibers. Okay. So the other approach is to take the ink again directly from the microfluidic processor and freeze it in a refrigerator, and we can then apply a vacuum, which causes, if we look at this phase diagram, we can perform this freeze drying process. So we freeze the water to ice, we apply a vacuum, so we are reducing the pressure, and then we let it heat up, and the water or the ice turns into vapor, which leaves behind a porous graphene structure. So here are some of the typical structures that we make. So these are now solid lumps. They're no longer an ink, but these are highly porous structures. They're lightweight, they are very low density, but they also maintain some conductivity because you have this framework of the conductive graphene, and they're relatively high strength as well. So if you look under a scanning electron microscope, you can really see this liquid crystal orientation, this alignment, and this white area, this sort of square shaped or column shaped structures are all the graphene that's left behind. So you're forming this nice sponge-like structure. Okay, so I mentioned graphene has this important property of electrons moving incredibly fast. But at the moment, we cannot replace silicon semiconductors because graphene doesn't have this gap, which means if you want to make a transistor, for example, you cannot switch it off. Okay, so you're always drawing power. So that's where other materials, so beyond graphene, we actually have we think around 2,000 materials, which are all layered in structure and can be exfoliated down to single layers like graphene. So where we have graphene as a conductor, I already mentioned a couple of others. We have insulators, we have semiconductors, we have some materials which could be superconducting and also thermoelectrics and many other properties. So the challenge, what we're trying to do now is build up unique structures layer by layer. So where we might have graphene with an insulator and a semiconductor to create some unique kinds of structures. So we call these van der Waals heterostructures. So again, this is highlighting another subset of these structures. So we have graphene down here, which can actually absorb all wavelengths of light, but you know, we have this middle range here, and we have the insulating boron nitride at the end here, which is absorbing in the UV because it has quite a large band gap. So there's many other materials in this regime that we want to play with, and we are playing with, which have many important applications, specifically in the electronic field and also optoelectronics. So they interact with light differently, and they can provide useful combinations with graphene and other materials. So if you're interested in reading more about graphene, so this is a review article called the Graphene Roadmap, and it's looking at the kind of next 10 years of graphene properties and production, and also looking at other layered 2D materials and how we will start to fit together a more complex vision to result in the commercialization of graphene products in many different fields, so you can find out more about different areas such as optoelectronics and energy storage, or the health and medical fields, and looking at how industry will play a key role in basically turning this from a predominantly academic research project into a more industrially focused one over the coming years. So this is a figure taken from that review article, showing the progress in kind of material properties that we're hoping to achieve over the next few years, and then down at the bottom some of the components or products that we hope to be able to achieve once we've achieved these targets and properties up here. So you can see at the stage we're at now, we're kind of in the regime of looking at roll-to-roll printing and high mobility materials, conductive inks, and that should help lead us to commercializing printed RF tags, foldable, rollable displays, and then as the years progress, we're looking at even faster electronics, wafer scale production, and looking at much higher end electronics, lightweight batteries, high performance energy storage devices, and then onto very complex spintronic devices for high speed computing. Okay, so in conclusion, I'd like to just state that microfluidic processing is really an effective and scalable high shear method to exfoliate not just graphene but many bulk 2D materials into few layer materials, and we can do that now in a very controllable way. The benefit of the process is it's very uniform. We can achieve very high loading inks up to around 100 grams per liter concentration. So that's much higher than we've achieved before with other graphene production techniques, and we can have a yield of 100%. So we can avoid some of the other lengthy separation steps that I didn't really discuss today. But essentially we can take these materials and we can develop versatile inks compatible with different printing processes, and also we can create some other functional architectures like the fibers and aerogel sponge architectures that I showed, which can have application in many other areas. Okay, so with that I'd like to thank you all for listening, and just to acknowledge some of the research funding that we have in Cambridge. And yes, I'd like to open the floor for any questions. Thank you.
Thank you so much, Steve, for that wonderful presentation. Now we will be going into the question and answers session of this webinar. So if you have any questions, please just ask them in the chat room of the Skype meeting. I did receive a few of the questions beforehand, so I'll start with those for you, Steve. And one of them is, do you believe that in order to separate the single flue layer of the larger GNPs, will it still require centrifugation in a washing stage to obtain a pure powder?
Yes, it completely depends on the process parameters and the end application. So most applications we find don't actually require producing single layer graphenes. But here I'll just show a few slides on. In fact, we can actually access these few layer graphenes. So one of the steps we've taken is we've looked at the process cycles of the microfluidic processor. So we even went up to 150 cycles, and then we performed this centrifugation step. So that's an essential step in the process. And now we are looking to find alternative ways of doing this separation, because it doesn't lend itself to being a highly industrial, scalable process. But essentially with AFM we can see we have these very thin sheets down to 1 to 2 nanometers thickness. We've done a whole lot of optimization of the process parameters and looked at different centrifugation parameters, as well as the microfluidic process pressures, and looked at the yields as a function of the starting graphene loading, graphite loading. But essentially, our yield for the process is limited to around 4 weight%. But that doesn't mean we're throwing away the other 96%. We are using the 96% for these other screen printing inks. So just some other numbers in terms of the scalability. So at the moment we are limited by this centrifugation step. So we have yields, production rate of around a few hundred milligrams per hour. And for the larger scale system, this might increase to around 10 grams per hour. But in terms of usable ink, that's still 65,000 liters of an ink that you can use for inkjet printing or other spray coating deposition techniques. So you don't necessarily need very high concentration to actually produce these transparent conductive films. Okay.
Yeah, thank you. Another question that we received was, what are the maximum temperatures a solid-liquid mix may reach inside the microfluidizer processing chamber after an hour of continuous processing using the highest pressure and the smallest chamber?
Yeah, so this is the reason we have to use the cooling system after the outlet reservoir, because if we process without any cooling, then the microfluidic processor, the chamber can reach temperatures of around 60 degrees, and that's after maybe a few minutes of processing. And then beyond that, every minute we tend to see an increase of 1 degree per minute. So after 30 minutes to 1 hour, we are potentially boiling our solvent inside the chamber, which can be detrimental to the lifetime of the system. So essentially, some processes may require some heating, and we have done some chemistry or chemical functionalization processes using slightly raised temperature, but we tend not to operate too long at these temperatures.
Great. How has the university done any evaluation of chemical effects using high shear?
Yes, well, the benefit is you get some nice confinement of all these materials through that interaction chamber. So we have done some chemistry and some functionalization of graphene and other materials inside the chamber. But I mentioned, yeah, of course, there are limitations. So we cannot operate these systems at very high temperatures, and also there are some chemical compatibility issues. So we cannot always put, some chemicals might interfere with the stainless steel of the different pipes, and also many of the seals inside. I understand we can change the seals to PTFE, which are more chemical compatible, but I think, it really depends on the type of chemistry that you want to do inside as to what you can kind of achieve.
Great. I think I can answer this one. We've got a question asking, does graphene or other materials cause wear or damages to the interaction chamber? And to put it simply, yes, but it really depends on the material and the hardness. Some materials will wear out the interaction chambers more quickly, but the interaction chambers are made of polycrystalline diamond or ceramic materials, so the lifetime is quite long depending on your batch sizes and how long you are actually running your processor, if that answers your question. Three-dimensional particles such as nanosized. Another one is, could the process be scaled to three-dimensional particles such as nano-sized diamonds?
Yeah, I think it's very simple to put nanodiamonds through the chamber, as long as the particle size to start with is already small enough. Maybe the aggregate size might cause a problem, maybe some blockages in the chamber. But I think it's certainly possible with the right solvent combination. Do you agree, Kelly?
Yeah, no, I completely agree. I think you are spot on with that. Are there any other questions? Could I use the Y chamber too? Yeah, so if you want to use the Y, we have optimized our chambers for the different applications. So the Y chambers are really more effective with your liquid-only applications, such as if you're doing a nanoemulsion of oil and water or water and oil. The Z type is really great for like this graphene or other applications, or like anything with solid particles. But there are instances where the Y chamber is used for the solid particle applications.
Yeah, I think for graphene production, ideally we want to produce the largest lateral size of graphene as possible. So using a Y-shaped chamber, you're kind of promoting impact forces, which might then fragment the particles too much. So that's why we went for the Z-type chamber.
Great. Another question we received was, you heat the ink to remove nanocellulose, which was also a binder. So after that, is the graphene still adhering well on substrates?
It does. So we have to, if we heat for too long a period, then we might start to see some delamination. But this is dependent also on the film thickness. So if it's a very thick film and we do heat for a long time, then yes, we do see some. But essentially, if around 30 minutes seems to be the sufficient time to leave the film on there and remove most of the binder.
Yeah. Thank you so much.
So you have a couple of questions there on the cost.
Yes, so if you do have any interest on any of our equipment, you can feel free to reach out to us individually, or I can also put you in contact with your local sales representative. One of the other questions we got was, have you tried any external cooling on the processing chambers and not only on the output?
I mean, we haven't, but I think you guys sell some cooling systems, do you?
I think they're asking about on the actual chambers themselves, and from our experience, it's not necessary, just for the fact that the material is only being processed through, like, it only interacts with the interaction chamber for a fractions of a second, so it's very small amount of time that it's actually in the chamber. So cooling around the chamber, we don't believe would have much of an impact. The heat exchanger would be much more efficient at cooling. So another one that we got was, how critical is the starting graphite lateral size with respect to the interaction chamber channel size, and what is the risk of the clogging?
Yeah, so this is something we had a problem immediately when we first used the microfluidizer. So we were starting with natural flake graphite, which is around more than 100 microns in lateral size. And we were putting it through a chamber which had around 87 microns diameter. So immediately we saw blockages, and therefore we kind of stick to something which is around 50 microns to start with. But of course you can use other chambers in parallel, maybe to do some initial particle size reduction. So you could use, for example, a 200 micron diameter chamber to do process your 100 micron size particles, so that they will then avoid blocking the smaller chambers.
I completely agree. So we're going to answer these last two questions and then wrap it up. And so any further questions, feel free to reach out to either Steve and I, and we'll definitely get back to you as soon as possible. So one of these last questions is, what is the shelf life of the ink?
So with the cellulose inks, it's about, well, over 1 year, I would say. And yeah, we selling many inks that we produced over a year ago. So they seem to be, they perform very well, and the same performance can be observed after around 1 year. So that's probably good enough for most scale-up processes.
That's great. Also, have you attempted to tune your system to over-process your graphene into graphene quantum dots?
Very good question, actually, because there is another paper from a group in Israel on the microfluidic processing of graphene quantum dots, so you might want to look at that paper. Yeah, so we do have some proportion which is very, very small, so less than 50 to 30 nanometers. So we can actually, if we were to centrifuge our materials at very, very high speed, there's always some fraction which is not actually sedimenting. and those are behaving like quantum dots materials.
That's great.
And in fact, yeah, we know we are over processing the material. After around 70 process cycles, we start to actually degrade the graphene that we're producing. So we actually see some. I can show one slide on this. If I'm still sharing my screen, yep.
Yep.
So if we look at the Raman spectroscopy, which is a very good method for graphene characterization, so we have the appearance of this D peak, which is a defect-induced mode, and that becomes very apparent after 70 cycles processing. So when we actually do some further studying, and this is probably the main expertise of our research group, is this type of spectroscopy. You find this, what we call correlation, between the intensity of the D peak and the G peak, which is essentially, you can call it the graphite peak. And what we contribute that means we are starting to put defects or functional groups into the surface of the graphene, rather than at the edges, which so the basal plane plays a key role in these properties, for example, the electronic and mechanical properties. So this is quite a critical piece of understanding, that we don't need to process more than 70 cycles. If we do, we start to then degrade the graphene material. Okay.
Yep. And with that, I think we'll be wrapping up the webinar now. Thank you everyone so much for your participation and attending this webinar. Thank you so much, Steve, for presenting all of your research and your work with us. If anyone has any further questions, please feel free to reach out to Steve or myself, and we can help you further with microfluidics technology or graphene and more. This is a recorded webinar, so we will be putting it into a video and make that available for everyone's future viewings. Thank you so much, and with that, we're done. Thank you.
Thank you.